Have you ever really wondered how the internet works? I mean, not just for checking your email, but how it looks to someone who needs to know its deepest, darkest secrets? All right, let's dive in and see the digital world through a completely different set of eyes.
So for this explainer, we're going to be digging into the fantastic book, Network Basics for Hackers by Occupy the Web. It's a really incredible resource that breaks down not just how networks are built, but also, and this is the interesting part, how they can be broken. Now, before we go any further, it's super important we get the mindset right here. We are not talking about criminals. The author is very clear, a white hat hacker is a force for good. They're someone who uses their skills to protect our freedom and privacy online. You can kind of think of them as the guardians of the digital world.
So, to get inside the head of this digital warrior, we have to understand the battlefield they operate on, and that is the network itself. This isn't just about some cables and Wi-Fi signals. It's a whole complex landscape of rules, addresses, and even a few secret passages.
Every single thing you send across the internet, whether it's a quick text or a whole movie you're streaming, it has a destination. So let's start with the absolute most basic thing. How does it know where to go?
The key to all of this is the Internet Protocol address, or, you know it, the IP address. And the analogy the book uses is just perfect. Think of it exactly like your home street address. Without it, the mail carrier, or in this case the data, would have no idea how to find you. Every single device that's online gets one.
Okay, now what's really cool is how this address is actually built. To us, it just looks like 4 numbers separated by dots, right? But what it really is a 32-bit number. Each of those 4 numbers is just the human-friendly version of an 8-bit chunk of ones and zeros, something called an octet.
So here's the problem. We ran into a numbers issue. There just aren't enough of these 32-bit addresses for every phone, laptop, and smart fridge on the planet. The solution? We have 2 types of IPs. Public IPs are your unique, one-of-a-kind address on the worldwide internet. But inside your house, on your Wi-Fi, all your devices use private IPs, which can be reused in millions of other homes and offices.
So how in the world do all those devices with private addresses talk to the outside internet? Well, it's through this really clever trick called network address translation, or NAT. Your router acts like a kind of gatekeeper or translator. It takes all the requests from your private devices, sends them out using its one and only public IP, and when the answers come back, it remembers exactly which phone or laptop to send them to. It's pretty smart.
Okay, so we know how to find a device using its IP address. We've got the street address. But once we get there, how do we start a conversation? For that, we need to have a set of rules, or as they're called, protocols.
And the big one, the most important set of rules, is TCP/IP. You can think of it as the official language of the internet. The IP part, the Internet Protocol, that handles the addressing, the where to go. And the TCP part, the Transmission Control Protocol, that handles the actual conversation. It makes sure all the pieces of your data arrive safely, checks for errors, and puts them all back in the right order so your message actually makes sense.
And I love how this slide breaks down how a reliable chat begins. It's called the 3-way handshake. It's basically a polite digital introduction. Your computer sends a little packet that says SYN, which is like knocking on the door and saying, hey, can we talk? The server on the other end replies with SYN-ACK, which means, yep, I hear you and I'm ready. Then your computer sends one last ACK packet back, which just says, awesome. And just like that, the connection is open.
This simple, really elegant little dance is the foundation of pretty much every reliable connection you make online. It makes sure that both sides are ready and listening before any of the important stuff gets sent. It's a digital confirmation. So our data packet, it's used the IP address to find the right building, it's used TCP to have a polite handshake, but which apartment is it supposed to go to? How does it find the right program on that computer?
And the answer is ports. The book's analogy here is just spot on. If the IP address is the street address of the building, then the port is the specific apartment number. It guides the data to the correct service, whether that's your web browser, your email app, or your online game.
Now, while there are over 65,000 possible ports, you really only need to know a couple of the main front doors. For example, almost all normal web traffic uses port 80, and the secure encrypted web traffic, that uses port 443. Knowing these common ports is absolutely fundamental for any network pro, or, of course, for a hacker.
And that leads us to a really crucial question, right? From a security point of view, if these ports are like doors into a computer system, how does an attacker figure out which ones are unlocked and, well, open for business?
Well, they use something called a port scanner. A famous tool for this is called Nmap. It basically goes to a target IP address and knocks on a whole bunch of doors, a whole range of ports, and then the system reports back which ports are open. But here's the kicker, it often tells you what service is running on that port. So it doesn't just give an attacker a map of open doors, it tells them what kind of lock is on each one, and maybe if that lock is old and easy to pick.
So we've seen how an attacker can find an open door. But to really understand all the different kinds of doors, and the windows, and maybe even some weaknesses in the building's foundation, we need to zoom out and look at the master blueprint for how all networks are built.
And this is it, the OSI model. This is the master plan for everything we've been talking about. Think about it. For a simple message to get from my screen to yours, it has to be created, packaged up, addressed, translated into signals, sent over a wire, and then completely unpacked in reverse order on your end. This model just breaks that whole journey down into 7 distinct jobs, or layers, from the physical wires at the very bottom all the way up to the app you're looking at on your screen.
And yeah, it's a lot to remember, but thankfully, the book gives us this super handy little mnemonic to keep the layers straight, from top to bottom. Just remember, all people seem to need data processing, application, presentation, session, and so on down the line. It's a simple little phrase that unlocks a pretty complex model.
And here it is. This is the big aha moment from a hacker's perspective. This model, it's not just some abstract theory in a textbook, it is a map of attack surfaces. Every single layer has its own unique vulnerabilities. Way down at the bottom, an attacker might try to sniff the physical layer to just listen in on raw data. In the middle, at the network layer, they could try a man-in-the-middle attack to intercept traffic. And way up at the top, they could use exploits to attack bugs in the application itself. Every single layer is a potential battleground.
And that kind of brings us to our final thought for today. We've seen that the entire internet is built on these layers of trust, from trusting the physical cables to the IP addresses we get, all the way up to the apps we use every day. So seeing it all laid out like this, the question isn't really if the internet is secure, but rather, which one of these layers do you actually trust the most?